Yes, indeed. So global kinetic models in the first place, and then with a focus that would be, for the large part of my presentation, spider pulsars. So what are these guys? What are spider pulsars? Spider pulsars are systems, very compact binary systems composed of a millisecond pulsar, spinning on itself on millisecond timescales, and a companion star. The companion star may be relatively low mass, less than 0.1 solar mass, degenerate companion, or a little bit higher mass, 0.2, 0.5 solar masses, non-degenerate companion. In the former case, they're called black widow pulsars. In the latter case, they're called redback pulsars. And you may be wondering why these weird names. I'm wondering that as well. The point is, the very first system, they realized very quickly that the pulsar, with its very relativistic, very powerful wind, was effectively evaporating the companion. So devouring the companion, and in the same way that black widow spiders are eating up, devouring their companions, their mates, they decided that these systems shall be called black widow pulsars. And then redbacks, which are also spiders, were a different type of that same system. So now that I've introduced them, I will argue that they are unique probes of pulsar winds. So the pulsar wind, as we all know, emanates from the pulsar. Beyond the light cylinder, the wind reaches relativistic speeds. This is the light cylinder. And the main property of the striped wind is that it's composed of alternating magnetic stripes. So you should really think about this magnetic field that's coming into the page, out of the page, into the page, out of the page. And all of this structure will be slammed onto the companion star, forming what's called an intrabinary shock. This will be the focus from now on, the physics of the intrabinary shock in this very peculiar systems called spider pulsars. And spider pulsars are a gift of nature to us also meaning PIC simulators. Why? Because as Heike mentioned this morning, the curse of PIC simulations, kinetic approaches in general, is the separation of scales. That very often the plasma scales are so much smaller than astrophysical scales that you need either very careful codes and very large computers, but even in that case, very often that's not enough. So why do I say a gift? Because everything I just said, the curse of the separation of scales, is not true for spider pulsars. The shock curvature radius versus the stripe wavelength. The stripe wavelength is the reversing, the wavelength of that reversing of the magnetic field, which is set by the light cylinder radius ultimately, is for typical parameters about 50. Our simulations are not really able to get quite there, but we're not very far. We're a factor of a few away from those conditions. The wavelength, stripe wavelength versus the post-shock Larmor radius, a factor of 30 expected to be in realistic systems, factor of 30 in our simulations. So we're not very clever. We're just choosing here a system that is naturally prone to be studied with PIC simulations, which are giving all of the physics of the dissipation, the particle acceleration, and yet you can capture the global scales, the global morphology of the shock at the same time as the microphysics of the dissipation. Hmm? That is very clever for those systems. Right, so this is a few words about the simulation setup. The companion is here. It's emanating an isotropic wind. This is the simplest configuration that is expected in realistic spider pulsars. This is the pulsar wind. So the pulsar, you should imagine very far away, sending its powerful, relativistic, strongly magnetized wind of alternating stripes. Positive in red, negative in blue. In this specific case, the stripe, blue and red, have the same thickness, the same width. This corresponds to a case in which the companion is sitting in the equatorial plane of the pulsar. You can see here, pulsar wind, same distance here as here. But if you're away from the equatorial plane, so if your companion is not in the equatorial plane of the pulsar, then these two thicknesses are not the same. The blue stripe and the red stripe will not have the same width. And this is a parameter that we vary by changing this parameter. This is a condition that we vary by changing this parameter alpha, which in other words is related to the net field that you have once averaged over one wavelength. The system is strongly magnetized. Magnetization is 10. We tried 40 as well. And let me give you the information about the dynamics first. This is the pulsar wind impacting onto the companion, which is that little white dot. The field is alternating, as shown by the white arrows, and this is how the evolution proceeds. This is already in a relatively good steady state for the system. The flow impacts the companion. It creates a shock. This is the intra-binary shock of the spider system. At the shock, these magnetic stripes get compressed. This is what a shock is very good at, compressing things, and it drives reconnection. So the process is called shock-driven reconnection because reconnection is really driven by the compression at the shock. Reconnection is a very good particle accelerator. The energy of the particle, the mean energy of the particle in this case, goes from the bulk Lorentz factor of the upstream flow up to sigma times larger than that. So in the case of complete dissipation, this is what you would expect. Energization brings the particles up by a factor of sigma. In addition to the physics of the particle acceleration, given that we do have a global simulation, we have the global dynamics, the global morphology of the velocity flow. This is what the velocity looks like in unfortunate color scheme. So the white is very low velocities. This is reached at the, this is achieved at the apex of the shock, and then as the flow goes around, it becomes faster, trans-relativistic velocities to the right and to the left of the companion. This will be critical for the emission signature that I'm going to talk about in 3.5 minutes. So what can we get out of this? Right? We have, in principle, everything. We have the dissipation physics. We have the particle acceleration physics. We have the global morphology of the system. This is the synchron spectrum that we get out in a band that is identified here as in between the two green dashed lines, which would correspond to the X-ray observing band. The spectrum is rather hard. Nu F nu goes like nu to the plus 0.7. Hard spectra are a natural outcome of reconnection. So this is not surprising. We have reconnection here. We have a hard spectrum, which is imprinted in the synchron spectrum. And this is consistent with X-ray data from real spider systems. Point number two, the light curve. The light curve is a little peculiar. In the case of alpha equals 0, so remember alpha is this parameter which quantifies how we're cutting into the pulsar wind. Alpha 0, we're cutting into the equator of the pulsar. The companion is sitting at the equator of the pulsar wind. The light curve shows two peaks, one right before and one right after the pulsar eclipse, the case in which the companion is between us and the pulsar. It's not just occultation by the companion. This would be on a much smaller temporal or orbital phase distances, but it's there. We'll see in the next slide why it's there. It matches the observations. Roughly speaking, the blue here corresponds to the cyan here. You see these two peaks in the X-ray light curve, right before and right after the pulsar eclipse. Why is that? Is because of the morphology of the shock and the post-shock trans-relativistic flow. So this flow of matter, which flows to the side of the companion, now is in the perfect directionality for an observer that is sitting up here or down here, such that the flow is moving towards the observer. Doppler beaming, Doppler boosting is enhancing the emission that the observer will see in the phases in which the flow is pointing towards the observer. So that's the effect. The two peaks are Doppler boosted emission due to the geometry of the flow around the companion. This is, it's not new here. This was suggested in the literature with semi-elliptical modeling. Alice has done a lot of work on that. But it's a confirmation that indeed this reality is happening within a global peak simulation. What we have been having in very recent months thanks to Andrew Sullivan, was Roger's student, Roger maybe even in the room, is to extend this to 3D. So everything I presented so far was 2D, and considerations and conclusions on the light curve and the spectrum are regardless of dimensionality, so they do hold in 3D as well. But 3D gave us the polarimetric angle, the capability to extract polarimetry, polarized emission. This is a bunch of 3D simulations. Again, we vary this parameter alpha, cutting into the pulsar equatorial, into the pulsar wind at different latitudinal directions. The magnetic field is in the plane in this slice, and then in this bottom slices, it's in and out of the plane. The simulations do reach a steady state. You'll see at the beginning that they're not quite in steady state, and then they get to a good steady state for pretty much all of the cases. But the main reason for doing 3D, as I said, is to extract polarimetry. So what do we get? The sweep in the polarization angle, which is in the bottom panels here for two different inclinations, 60 degrees versus 90 degrees, is not surprising. This is just a statement of the fact that the dominant field component is the toroidal field in the pulsar wind. Some of it is destroyed post-shock, but the main orientation is preserved, basically, as compared to what it was in the upstream. The thing that is not very easy to get from analytical modeling or semi-analytical modeling is the polarization degree shape, which is shown here. What the simulations show is a significant degree of polarization, 15 degrees or more, which increases as you increase this stripe averaged field, so the value of alpha. This is, as far as I know, not yet observed with XP, but soon to be observed, or it's being observed now. Hopefully, we won't be falsified very soon, but we'll see. So now I would like to broaden the scope of my presentation a tiny bit and discuss global kinetically motivated models of relativistic sources. And now this is a very broad title. Let's narrow it down. We do, as a community, routinely global peak simulations, and there is absolute value in doing that. At the same time, they suffer from this curse of the scale separation. So very often the technique that is used is MHT, but MHT comes with its own limitations. So I will try in the next few slides to convince you that maybe one of those limitations can be overcome. So what is that limitation? That limitation is the so-called reconnection rate problem in relativistic reconnection. Relativistic reconnection, as introduced by Hayek this morning, is this process of annihilation of magnetic fields. Relativistic is a statement about this sigma parameter, which I already introduced for the spider pulsars, much larger than one, more magnetic energy than rest mass energy of the particles. This is the Wikipedia picture and insight, if you want. If you want a little bit more, you can read this review that we wrote with Dima and Dimitris Giannios recently, with vital contributions by several people in the room, Hayek, Luis, and a few people that are not in the room, Benoit and Antao. So what is this problem? The problem is the fact that MHT gives a different rate of magnetic field dissipation than kinetic calculations. In MHT, the inflow rate of plasma into the dissipation region is 10 to the minus 2 of the Alfvén speed. For relativistic conditions, this Alfvén speed is the speed of light, so 10 to the minus 2 of the speed of light. For equivalent kinetic calculations, this was shown to be instead 10 to the minus 1 of the speed of light. Is this a problem? Is this not a problem? And you might say, it's not a problem. These are different frameworks. They're solving different equations. The Ohm's law, more specifically, is very different. This is the collisional relativistic Ohm's law. This is the collisionless relativistic Ohm's law. Collisionless has much more many more options for breaking the flux freezing conditions. So why should they give a different, the same reconnection rate? Yes. right? And yet, we use MHD very often because that's a very good tool to use for systems that are naturally collisionless. So we're using, in some sense, a good tool for the wrong system, or the wrong tool for a good system. So what is the way, or one way, to overcome this? And again, this is restricted to the problem of reconnection, and reconnection in relativistic systems. So what about finding some effective resistivity, eta effective, that could be used in MHD to give, at the same time, the correct reconnection rate as prescribed or as captured by a kinetic approach? Work on that in the space physics community, I think, has spread over decades. Here, we're just tackling this for the specifics of the relativistic systems, so in which reconnection is relativistic. And the prescription we came up, which, let me remark, needs to be using quantities that MHD needs to know about, is based on the following argument. So the first one is just Ohm's law. So the non-ideal electric field, which is defined this way, is just eta times J. It's a definition of eta, if you want, or Ohm's law. And the second one is, at X points, these are the regions where the magnetic field reconnects and dissipates. We postulate that the current is charge-starved, which means that the magnitude of the current is just the elementary charge times how many particles you have per unit volume times the speed of light. All of them are moving at the speed of light. That's the assumption at X points. So if you do that, then you come up with a resistivity that has this form. First question, does it work within PIC? So in PIC, if you compare the ground truth to the reconstruction using this resistivity, does it work? And this is work done by my student, Abby Moran. This is the ground truth of the non-ideal electric field. This is the reconstructed value. Eta times J, not bad. Okay, but we go one step further. Now you put it in relativistic MHD. Does it produce the right physics that a collisionless approach would produce? And we did two tests. First one is a local test of just a basic Harris layer. This is the prototypical reconnection layer. The plot you have on the left is uniform resistivity. The two plots you have on the right are the peak-motivated resistivity that I just talked about. Healthy plasmoid chain on both cases, but the magnitude of the electric field, which is honestly fundamentally a statement about the reconnection rate, is different. This is visibly much smaller and more disorganized as compared to this one. We'll see it more quantitatively in the next step. And finally, a global test, maybe the simplest global test. This is black hole balding. The left, once again, uniform resistivity. The right, peak-motivated resistivity. The movie is not running yet, don't worry. The top will show the magnetization. The bottom will show the polar velocity, which means the velocity converging into the equatorial plane. And you will see reconnection here happening. Reconnection is the way the black hole is losing its magnetic here. Again, a probe of the reconnection physics, a probe of the reconnection rate in maybe the simplest global problem. This is work done, by the way, with several people in the room, Michael, Sasha. I encourage you to listen to Alicia's talk tomorrow or Thursday as well for more details regarding this prescription for the radiative reconnection case. So this is how it looks like. Once again, healthy plasmoid chain in both cases, as we also expect from PIC, but the polar velocity with the peak-motivated resistivity significantly higher in the direction of bringing MHD to peak values, to collisionless values. And this is my last slide on the quantitative comparison. This is the local test inflow velocity over the speed of light. So a statement about the reconnection rate as a function of time. This is what uniform resistivity in MHD would give, 0.03. This is what PIC, yellow, orange, and the non-uniform PIC-motivated resistivity in MHD gives. And they're on spot on top of each other. Global problem, similar success. Slow decay of the magnetic flux onto the black hole. In the case of uniform resistivity, 0.02, corresponding to a reconnection speed of 0.02. If you are using the non-uniform PIC-motivated resistivity, it becomes over 0.1. Ashley, Sasha in 2021 did it with GR-PIC as well and found exactly a 0.1 rate for this problem as well. So I'm closing it here. Since by now you forgot about spider pulsars, my summary is only about spider pulsars, and I'll stop it here. Thank you so much.
Thank you. Are there questions? Yes.
Okay, yeah, thanks, Lorenzo. Great results on the spiders. But most spiders actually have the shock wrapping around the pulsar.
Yes.
So do you intend to do that case as well? And what do you expect would be the differences?
It's a great question. The answer to your second question is I don't know what would be different. Yichi, actually, who is in the room, has done some work that may be more applicable to even though her emphasis was not on spiders, but it may be more applicable to conclusions that are related to redbacks. But you're absolutely right. The assumption here is that the pulsar wind is more powerful than the companion wind, such that the shock is wrapping around the companion rather than the other way around. This is the configuration that is expected for Black Widow pulsars, and on the other hand, the configuration that you mentioned, in which the companion wind is more powerful than the pulsar wind, is more typical for redback pulsars. And that's yet to be done. The other thing that may be interesting to explore is whether there is any difference in the conclusions in the case that the companion is just emitting an isotropic wind and stopping the pulsar wind with this isotropic wind, or whether there is a magnetosphere that is stopping the pulsar wind itself. I think that's still very much in the works.
Yes.
Thanks for this very nice talk. I was just wondering, so for the charge starvation argument, I understand that it works in the X point, but why can you apply it to a global simulation that is much more than just an X point or just a current sheet?
Question. So the argument would work there, and the resistivity is not that large everywhere else because the E star, the non-ideal electric field that is in the numerator, is 0 everywhere else. So in some sense, it localizes the resistivity in the places where the non-ideal electric field is non-zero. And in those places, which happen to be the X points, by and large, the assumption of charge starvation is correct. So it's not a statement that charge starvation is true everywhere. It's a statement about charge starvation happens in the region where the non-ideal electric field is important.
Why was E star non-zero in MHD to begin with?
Why was
E star non-zero in MHD?
So we always have, well, the ideal MHD everywhere is non-zero. That's true.
No, it's 0.
It's 0 everywhere, yes.
Right. But you already had the resistivity, right?
There is always, in the calculations of the non-uniform resistivity, there is always a baseline, uniform, very small resistivity.
So you're amplifying numerical fluctuations, or like?
The E star is constructed as part of the evolution of the system, so I don't think you can call it like numerical fluctuations. But maybe I'm not getting in.
Do you have explicit uniform resistivity?
There is an explicit, very, very small uniform resistivity in the MHD calculation as well. Yes. So in the places
is it
where
bigger than numerical resistivity?
It can be controlled, but it does not matter. I think if the question is, let me try to disentangle the question. So if the question is whether you need any resistivity anywhere else, you can do it with purely ideal MHD, and that's fine. But in the X points or in the regions where the resistivity is activated due to numerical reasons or due to a background resistivity, whether that's the numerical resistivity or it's the background very small resistivity, it does not really matter, because this one will win anyway in those regions, and then it sets the reconnection rate.
Can you do this in non-relativistic?
Oh yeah, the good question. Yeah, I don't know. The non-relativistic reconnection, as we know, Anatoly had a paper with a student just a few days, a week ago, is intrinsically very different. It's not plasmoid dominated. So one of the targets that we had in claiming success here was the formation of a healthy plasmoid chain. So I am not sure what target I would be claiming as success in that case. I have data in which I have extracted resistivity, a prescription in which you're just replacing the speed of light with the Alfvén speed seems to be working okay from the point of view of PIC, comparing ground truth with the reconstruction. But we are very far from claiming that this would work in an MHD non-relativistic case. Yes, upstream Alfvén speed. Yes, inflow Alfvén speed, yes.
So there's some interesting phenomenology about the eclipses, like you see the Coriolis force bending the eclipsing material. So it has to be dense, and yet you look at the electron column, and it doesn't seem to be dense enough. So do the electrons at the boundary layer between the wind and the pulsar wind get relativistic, or?
That's a very good question, and I cannot really answer that because our our companion wind is very unrealistic. So the way we set up the companion wind is just to stop the pulsar wind. I would be very careful about drawing any conclusion, even at the interface, because that would matter what kind of companion wind we're putting in. In very practical terms, like we don't want to spend peak power in the companion wind, and so instead of having a very dense, very non-relativistic wind, we have a relatively dilute and relatively fast, unrealistically fast companion wind.
But as you know, of course, there are an increasing number of Faraday measurements and lensing measurements and so on.
The lensing part is very interesting, and I think I agree. I think it's a very, very interesting problem. I would say for that part of the problem, hybrid strategy in which the companion wind is not really modeled with particles should be used.
So I think it's worth emphasizing for the audience that these are very interesting systems, and that the waves frequency, isn't too far above the critical frequency or the gyro frequency in the ambient plasma. So it's an unusual situation astrophysically, and lots of interesting, collective effects are likely to be occurring. Yeah.
Thank you, Lorenzo. I have a question about your prescription for resistivity. How exactly does it work? Yes, like Anatoly, somewhat not clear. And do you turn it on in some region?
No.
What's the condition?
No.
So how does it?
So the MHD
algorithm.
Yeah, the MHD prescription, okay, has, if you want to think about it as like even simpler so that we don't rely on numerical resistivity, there is a baseline, very, very small uniform resistivity. And then this one is activated whenever this is larger than the other one.
So that uniform resistivity is uniform, right? So the condition on that electric field is the same as the condition on current density. That's right? On local current density. I mean, is it equivalent to saying that the current density exceeds some threshold?
Yes, it's equivalent. Yeah, it's equivalent.
I'm asking this is because I know in solar physics, people have been doing a prescription where there is effective, again, MHD simulations with resistivity.
There is a function of J.
As a function of J, right? It's a threshold of that rapid growth.
So the major difference, I would say, there are many differences with the non-relativistic case. Okay, so first one, I guess, as I said, C cannot be C, but it needs to be the Alfvén speed if you're using this. The second difference, which is an algorithmic difference, In relativistic MHD codes, the electric field is a dynamical variable. So you are solving for its evolution. So you're using Ohm's law to obtain not the electric field, but a current. And then you're plugging the current into Maxwell's equations and you solve for the electric field. So a prescription of a resistivity that uses E star, the non-ideal electric field, is perfectly valid because you're not using it to compute E star. In the non-relativistic case, this is not true. The electric field is not a dynamical variable. So that's a major difficulty of applying this straightforwardly to the non-relativistic case. Third thing, that prescription is not just E star, is E star divided by the density. And the density dependence is actually critical. So you do have density depletion near the X point, which localizes the resistivity there because of the density drop. So you would be equivalent, possibly, to having a prescription that is not just J to some power, but J over density to some power. And I do not know whether this has been tried.